Okay, let's make a start. So today we're gonna see lecture 4, and that's about sorting. So again, what we have seen so far is how to analyze algorithms, and then we have seen some simple data structures like stacks and queues, and some concrete data structures like linked lists and arrays. So what's sorting really? Sorting is basically we have a sequence of elements, and what we want is to make these elements in order from smallest to largest, or from largest to smallest. Now, I think we have started. So can we have some peace and silence, please? Thank you. So when we sort elements, these elements can be anything which we can compare to each other. So we can sort, for example, we can sort integers. So a sequence that we want to sort can be, for example, 1, 4, 0, etc. So that's a sequence of integers. So we said that sorting, the problem of sorting is where our input is a sequence of elements. So in this case, the sequence is I think so.
Lab 3 only.
Lab 3 only? Yes. Yeah, we are fixing that. Okay, let's start again. So today is lecture 4, and we are going to see sorting. So everybody hears me now? All right. So what is sorting? So basically, in sorting, what we have a sequence of elements, and we want to order these elements from the smallest to the largest, or from the largest to the smallest. So if our sequence of elements is 1, 4, 0, then, and our sorting is increasing, then, or we are sorting these elements in increasing order, then the result of sorting this sequence is 0, 1, 4. So we want to study algorithms that are going to help us do the sorting. So we get a sequence as input, which is not sorted, and our objective is to sort it from smaller to larger, and our objective is to sort it from smaller to larger, and this is like sorting in increasing order, or from larger to smaller, largest to smallest, and this is called sorting in decreasing order. Now, the sorting takes as input a sequence S of elements. These elements can be integers, like shown in the slide here, like 1, 4, 5, etc. It can also be a sequence of arbitrary records. And in order to compare the records, we are going to choose one of the fields in the record and use it as a key. So what does that mean? So we can sort elements of integers, like we said, for example, 10, 11, 3, and the result of sorting this, for example, in increasing order, will be 3, 10, 11. We can also sort sequences of records. Let's say we have record 1 of a student. Let's say it's called student 1, and the record contains data about the student. Let's say the student has got a GPA of 4, and the student has got an age of 20, and the student has got a name which starts with an A, and so on and so forth. And another student 2, the student 2 has got GPA 2, has age 19, and the name starts with M dot dot dot, and we want, and let's say that we have more of these students, 100 different students, like students taking the course data structures and algorithms, and we are going to sort them from smallest to largest. Now, how do we do that? The student is a complex data structure. It's a record. It's not a scalar or primitive data structure. So we need to agree on how we are going to compare the two records. So are we going to sort students with respect to their GPA? So are we going to sort students with respect to their age? Are we going to sort students with respect to their names, etc.? So these are different ways we can sort the students. Now, let's say that we want to sort students in increasing order with respect to their GPA. So which student comes first? Is it S1 or is it S2?
The last one. The one with the mystery.
So this one comes first, S2, right?
The last one. The one with the mystery.
So this one comes first, S2, right? Because we are sorting in increasing order. Now, if we are sorting in decreasing order with respect to the student's name, which one goes first? So we want to sort in decreasing order with respect to the name. Which one goes first? Which student? Student 2, yes. So student 2 is bigger than student 1 because the name here starts with an M, and this one is bigger than the name which starts with an A. We call this the lexicographical order. Lexicographical order is the ordering of strings. So A comes before M, and hence M is bigger than A, and hence student 2 is bigger than student 1. So this is what I meant by using a key. So S1 is a record and S2 is a record. Each one of them contain fields. And we have to specify one field and use it for comparison. So when we want to sort a sequence of elements, and they are records, a record is a collection of fields, we have to specify which field we are going to use for comparison. This field that we are going to use for comparison is called the key. Okay, so back to the slides. How do I go back to the slides? So what I'm saying here is when we have a sequence as integers, obviously we can just compare them. When we have a sequence of arbitrary elements, then we are going to use the key of the element. So element EI of some sequence, E1, E2, like student 1, student 2, we are going to choose which field, like name, age, GPA, and this field we are going to call it the key. It is going to be different in different sorting problems, obviously. So if I want to see the class from the most brilliant student with the highest GPA first, then I use with respect to the GPA. If I want to print the students from alphabetically, I use the name as the key. If I want to print them with respect to the date they joined the university, I'm going to use the field which shows the date they joined the university. So depending on what we want to sort, we are going to use a different key. But before sorting elements, we are going to use the key. Okay? Now, if the sequence of elements is a sequence of integers? Now, what is the key here? So these are three elements. That's one element. What's the key? It's the element itself. Okay, if it's a record, we choose which field. If it's a scalar type like that, it's it's 1. Then it's the element itself. Now, so this is what sorting trying to do. So the input is some sequence S of elements. The output is some sequence S prime of elements where S prime is a permutation of S. Okay, so if we are sorting 10, 20, and 5, then the output is a permutation of that. It's 5, 10, 20. So the input is a sequence, the output is a permutation. However, this permutation satisfies this condition that the first element is smaller than the second, which is smaller than the third, etc., assuming sorting in increasing order. So throughout this lecture, we are going to assume that the sorting algorithm is for elements of is of increasing order. So smallest element first and largest element last. And we are also going to use integers to show our sorting algorithm. But the results are also applicable to sorting in descending order, and they are also applicable to sorting sequences of arbitrary elements, i.e. not just integers. Now, does that make sense? It's the easiest slide in the lecture. It should make sense. I mean, that's like a rhetorical question, really. It's some easy stuff, really. Maybe you're still in holiday mood. So, sorting, we have a sequence of elements, we sort it, and we get it sorted. I don't think it can be easier than that. So, moving on. Sorting can be used in different problems. For example, the selection problem. Now, if I give you a sequence of elements, and I ask you the question, what is the kth largest element in this sequence? So I give you a sequence of elements 20, 5, 10, 7, 3, and I ask you what is the second largest element. So what is the second largest element in this case? So it's 10. So in order to solve this problem, we have to sort the elements from the largest to the smallest, and then we are going to pick element number 2. If we are trying to find the fourth from the largest to the smallest, and then we are going to pick element number 2. If we are trying to find the fourth largest element, again we sort them from largest to smallest, and we pick element number 4. So sorting is used to solve the selection problem. Another problem we can think of where we can use sorting is the closest pair problem. So we have a set of numbers, and we want to find the pair with the smallest difference between them. So in the example above, in this example here in front of you, what is the pair of elements with the smallest difference? Well, a pair. So 5 and 3 or 7 and 5, right? So there are 2 pairs here. So the way we do that is again to sort elements, and then we are going to compute the differences between adjacent elements in the sorted sequence. So we sorted 3, 5, 7, 10, and 20, and then we are going to look at every 2 adjacent elements and compute the difference. Obviously, the first elements, after sorting from smallest to the largest, we will be able to extract which pair of elements has got the smallest difference. I still hear some talking. I mean, could you please concentrate? I'm not going to go through this again. And understanding this is essential for understanding the rest of the lecture. So this is the easy stuff, but we need to know it because the lecture later on will get really complicated. So don't push me to make this part of the midterm because I can. Okay, so we better concentrate. Okay. So and there are other problems where sorting is of many. I mean, is of great use actually, when you start programming significant projects, not just for your homework, you will find that the only way you can make use of some data is when it is sorted. You always need, you're dealing with a lot of data, you need it sorted in order to be able to do something about it. To implement efficient search, for example, if to search for something efficiently, like using binary search, you need it to be sorted, etc. So sorting is something that you will always need to do. And because you will always need to do sorting, we need it to be very efficient. And to make it very efficient is what we are going to study in this lecture, different sorting algorithms. Why some and to make it very efficient is what we are going to study in this lecture, different sorting algorithms, why some of them are good, why some of them are not good, etc. So we are going to look now at the first sorting algorithm. We call it selection sort. Okay, so first sorting algorithm is selection sort. The best way to visualize how the sorting algorithm works is via an example. But before that, let's just explore what this sorting algorithm is about. So selection sort works by repeatedly selecting the smallest element from the unsorted part and adding it to the beginning of the sorted part. Okay. Now, what does that mean? This is our initial sequence. So we are here. This is the sequence that we are going to sort. It has 10 elements. You see the slide, right? Right. So how are we going to sort this? The objective is to sort the sequence in ascending order, in increasing order. So what happens at the end of the sorting is that we get the sequence 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. So what do we do actually in the sorting algorithm? We are going to look at the first element of the sequence. So we look at the first element of the sequence, which is 9. And then we are going to traverse all the array or all the sequence to the right. And we are going to try and find the smallest element in the array. Okay, so we pick the first element. Here it's shown in it's shown in red. And then we search for the smallest element to the right. So the smallest element to the right is 1. So we are going to search 4. So we say 4 is the smallest element so far. And then we move to 8. Well, it's not. 7. No, 4 is still smaller. 1. Yes, 1 is the smallest element so far. So then we mark 1 as the smallest element. And then we move to 6. It's not smaller than 1, 2, 10, 5, 3. They're not all smaller than 1. So then we find out that 1 is the smallest element. Now, question for you. What is the complexity of searching for the smallest element? Yes, it's linear. If we have an array of size 10, then we have to move through all 9 cells. So we're going to need 9 steps. If it's 1,000, we're going to need 999 steps. So it's linear. So as we said, we look at the first element, we mark it in red, like in this case, and then we look at the smallest element to the right. We said we look at the first element, we mark it in red, like in this case, and then we look at the smallest element to the right. In this case, it's 1. It's marked in green. Now, once we find it, we do a swap. So 9 and 1, they swap places. So we get 1 here and 9 here. So we have swapped them. Okay? Now, we pick the second element and we mark it as red. And then we try to find the element which is the smallest to the right. Okay? So in this case, what is the smallest element to the right? Yeah, it's in green. 2. So we find that it's 2, and then we swap them. So we get we swap 4 and 2, and we get 2 and 4. They are marked as blue, and then we continue this. We pick the third element, which is shown in red, 8, and then we try to find what is the smallest element to the right. And the smallest element to the right is 3, so we make a swap between 3 and 8. And we repeat it and we make a swap, and we continue doing that. So we continue doing that. We get to this stage, we find 6, and then we try to find the smallest element to the right of 6. There is no element, so nothing changes. So we move to the next one, 7, and we try to find for smallest element. It's actually 8. Sorry, here it's 7. That should have been in green, but it's not smaller than 6, so there is no swapping that happens. And here it's 8, but there is no swapping that happens. Now here it's 8 again, but there is some swapping that's going to happen. And finally 9, but this is 10 is greater than 9, and so no swapping happens. So if we look again here, I have a question. I said that every time we are going to mark one of the elements in red, and we are going to search to the right for the smallest element with which we can do the swapping. Now, why do we look to the right? Why don't we look to the left?
Because the left is order. Sorry.
Yeah, because we have already sorted these elements. Because to the left, so what we are doing essentially in this algorithm is we are finding the smallest element, and then the next smallest element, and then the third smallest element, the fourth smallest element, etc. Okay, so that's why we don't need to look to the left. So this is how selection sort works. So as you can see, we start. So we start, these are iterations of a loop that we are going to see. So we start with the first element. So I equals 1 means the first element. And then we are going, so there is a loop that is going to take us from the first element to the second element, to the third, to the fourth, to the fifth element, etc. There is a loop. And inside this loop, we are also going to visit each element to the right of the current element. So in the first iteration, we are going to visit these elements to the right of the first element. In the second iteration, we are going to visit these elements to the right of the element, to the right of the second element. In the third iteration, we are going to visit these elements which are to the right of the third element, etc. So we have two loops. One loop is going to take us from element 1 to 2 to 3, and inside this loop there is another loop that is going to help us traverse the elements to the right of the current element. And this gives us the code of selection sort. So our input is some array which is non-sorted. So what we are going to do, we are going to look at all the elements from the first element to the second last element. So if it's an array of length 10, we are going to loop from 1 to 9. Okay, we are going to mark the minimum as the current element. Okay, so this is minimum equals I, means the minimum element is actually stored at the index I. And then we are going to look to the right of the current element, and that's why we are going to look from I plus 1 to n. So if the second element, we are going to look at elements from 3 to 10. If it is element number 4, we are going to look at elements from 5 to 10. So elements which are to the right. This is the second loop, which is actually traversing the elements to the right. Whenever we find an element which is smaller than the current element, we are going to mark it as the minimum element. Finally, after everything, we are going to make a swap like we did here. Once we find an element which is smaller than the current element, we are going to swap them like that. So this is insertion sort for you, selection sort, sorry. That's selection sort. And we have seen an example. So by looking at this code and looking at the example, you can understand how this algorithm operates. Now, if you still cannot understand, this is the same version, but with comments to help you understand in case you missed something in the explanation. So this is selection sort without comments.